Okay, so what we're going to do now is we're going to look at the properties of the linear Schrodinger equation. So we're going to study this. So it's linear, which is great, but not simple. Okay, so what is a linear Schrodinger equation? It's basically, okay, let's not do dx squared w, this is how I'm writing it, plus uw equals minus lambda w. So it's basically an eigenvalue equation for a second order dE. So when you did the heat equation and you separated variables, you ended up with u is equal to 0 and you solve it with some boundary conditions. So we're interested in the case where x goes from minus infinity to infinity, and we're interested in where the case where u goes to 0 as x goes to plus or minus infinity. We actually want u to be bounded in some way, but you know, so the integral of u to be bounded or something like that. But we just want it to go out. Okay, so u is a parameter in this equation. Now, if you've got any sort of quantum physics, you know about how this is written in a funny way, because I'm going to just draw it here. So I suppose this is my, I was stupidly trying to muddled up the, let's make this u, and this is x. So what happens is that clear the page. I'm going to change the color. So this is in quantum physics. Out here, this region here, these are the free electrons. So they can sort of travel along here, and they're traveling like waves. Okay, so u is equal to 0, and the solution is w must be something like e to the ikx. Okay, we'll come to that. What k, you can sort of see what k is equal to that. It's going to be the square root of lambda or something like that. And then, so these free electrons, and then they're going to, when they come and encounter this thing here, they're going to bounce. So some are going to be reflected and some are going to be transmitted. Now, in this region here, you've also got trapped electrons, and there's a finite number of trapped electrons, and it's a bit weird because this u goes up positively, whereas normally we think of things getting trapped because they're falling down, but it's just the way, it's a sign we've drawn it with. So in here, this is lowering the energy. So in here, there's a finite number of trapped. And if you've done any finite number of trapped electrons, okay, and then outside here, these trapped electrons go as e to the minus kx. Okay, they decay exponentially. So the k here corresponds to a different sign of lambda. So if you think about it, for this to match up, over here, when I differentiate, u is 0, right? This is in the u is equal to 0 region. So over here, if I differentiate this twice, I'm going to get minus k. So over here, I get k squared is equal to minus lambda. Okay, so lambda has to be negative over here. And here I get minus k squared is equal to minus lambda. Okay, so lambda is positive. So these free electrons here, lambda is greater than 0. And these trapped ones, lambda is less than 0. Okay, so we're just going to basically do some calculations and work out. So for an arbitrary curve here, you can't calculate. And we're going to do some calculations, and we're going to work out what what these k's are, determine these k's. Or in the case of the free electrons, the reflection coefficient varies with k. We've got to calculate that. And it turns out that somehow there's a deep connection between this and the KdV equation, which we'll talk about in the following lecture. The only thing to say finally on this KDV and about the Schrodinger stuff is there is if this thing here, this U is equal to the soliton, something very mysterious happens and the reflection coefficient is 0. I'm not sure if that was known when they spotted this connection or not, but something very deep goes on that if this is most potential wells are going to reflect and not everything's not going to pass through, but if it was a soliton's shape, it'll actually pass through. What we're going to do now, we're just going to calculate a few of these, simple examples, and then you're going to do some computations of those yourself, calculate.